Okay, so hello everyone. My name is Anna, and today I'm going to talk about a little bit of the James Webb Space Telescope as part of the AstroCamp series of lectures. So, what? Okay. So when you gaze into the night sky, what you may think you see is a distribution of stars or galaxies separated by darkness. But in reality, that is not what is really there. And that is where the concept of deep field imaging came to change astronomy. So, what are deep fields? Deep fields are long exposure images that are intended to reveal faint sources. So basically, you point the telescope to a region of the sky where there is no visible light, and you let it stay there for a lot of time, and then faint sources start to appear. And of course, the first deep field image came with the Hubble Space Telescope in 1995. And this was the first time we could actually see distant objects that are very faint and that otherwise could have not been observed. And because the speed of light is finite, the more distant an object is, the further in time it is. So we are actually looking at the past. Of course, you may think, oh, this is just a region of the sky that has an unusual number of extra galaxies. But so what was done in 1998 was pointing the telescope to another region of the sky, in this case, the southern hemisphere, and it was found that this population of distant faint galaxies still appeared. And deep field imaging is not exclusive to visible light. So X-ray deep fields also exist, in this case carried out by the Chandra Observatory. And not as impressive as the ones carried out by Hubble, but in this image we can see a lot of black holes. And at last, in 2006, we had the Hubble Ultra Deep Field, which is the deepest image we can get in optical light. But why is it the farther we can get? It's because Einstein's theory of gravitation tells us that the universe is expanding. And so light is actually being stretched out and shifted to a longer wavelength. And so when we are observing distant objects, we're not actually seeing their visible light. We're seeing their visible light or their ultraviolet light shifted into infrared wavelengths. And that's the true reason why we need infrared telescopes. And so an attempt was done with Hubble and also with the Spitzer telescope to do infrared deep fields. And this is a result, but this is limited. And so on the basis of these discoveries, the James Webb Space Telescope appeared. So as we can see in this image, the Hubble Space Telescope does astronomy in the ultraviolet, in the visible, and a little bit in the infrared wavelengths. But the James Webb Space Telescope primarily focuses on infrared wavelengths. And so with this unparalleled infrared sensitivity, we will finally be able to focus on studying distant objects that emit in infrared wavelengths. And this is important to astronomy because a lot of astrophysics open questions involve infrared wavelengths. So like distant galaxies, faint comets, etc. I will explain this a little bit later. So the James Webb Space Telescope was launched on December 25 of last year aboard an Ariane 5 rocket, and it was launched on the ESA launch site, which is in French Guiana. And here we can see the last image of the James Webb Space Telescope. as it was separating from the Ariane 5 rocket. And so now I will walk you through it, basically the timeline from launch into orbit. So the rocket was launched, the Ariane 5 rocket was launched. Then basically 26 minutes into its trajectory, it was still being, the telescope was still using thrust from the rocket. Then the launch vehicle finally separates. And then about 33 minutes into its trajectory, the solar array finally deploys. And so what this means is that the telescope is now producing electricity and using that electricity, that solar electricity, in its motion. So 14 hours in, we have a mid-course correction, and then the sun shield starts to deploy. So I don't know if you can see it, but the sun shield is that gray 5-layer thing. And the sun shield is very important because this is an infrared telescope. And so we need to protect the telescope from any sources of infrared other than the object we are observing. So that means heat from the sun, earth, moon, etc. So the sun shield has that function of protecting the telescope from light and heat. Okay, then we continue with the deployment of the secondary mirror, then the primary mirror. And then finally, nearly after a month, the James Webb Space Telescope reached the second Lagrange point where it is in orbit. So I'll explain a little bit about the orbit. So basically, the telescope is orbiting around the Sun-Earth second Lagrange point. And that means that it's in synchrony with Earth's orbit around the Sun. So the telescope is at a constant distance towards Earth. And that is ideal for a variety of reasons. But first, the sun shield is always facing towards the Earth and the Sun. And so it is always protecting the telescope, which is ideal for observations. And moreover, the telescope is always avoiding the shadow of the Earth and the Moon. So we can do scientific missions 24/7. As you will see later, that is not the case with the Hubble Space Telescope. Also, we have uninterrupted solar power and communications to Earth at all times. So this is the ideal from a scientific mission point of view. So I already talked a little bit about the primary mirror, which are the yellow gold hexagonal shapes, and the sun shield. Sorry, the mic is here. But what really matters in the James Webb Space Telescope are the 4 instruments that are there and that will enable the scientific missions. So there are 4 instruments on the James Webb Space Telescope that allow for imaging and spectroscopy, and that they all work in the infrared. So first we have the near infrared camera, and this is the primary imager, and this works between the wavelengths of 0.6 and 5 micrometers. And the good thing about this camera is that it has something called a chronograph, which I can go into detail later, but basically it will allow astronomers to take pictures of very faint and dim objects, okay? And this is what we want. So in the same range of wavelengths, we have the near infrared spectrographer. So this is what will allow to study mass, temperature, chemical composition, and to basically to do slit spectroscopy. We also have the near infrared imager with the fine guidance sensor, and the fine guidance sensor is crucial. So what the fine guidance sensor does is it locks into a star, and it ensures that throughout the entire observation, Hubble is locked into that star and not losing track of its orientation. And then we have the mid-infrared instrument. And as you can see, this instrument works deeper into the infrared. And this is what we want, because we want to be able to peer through dust. Dust is a reoccurring problem in astronomy, and this instrument will be able to solve that. Okay, so now just a brief comparison with the Hubble Space Telescope. So not only do Hubble and Webb have different technical capabilities, but they also have different scientific goals. So the Hubble Space Telescope was designed as a general purpose observatory, so to observe galaxies, planets, and stars. But Webb, has a specific mission, and that is to study infrared astronomy, basically. But regarding the technical capabilities, we can see that Webb has a primary mirror that is much larger than Hubble, and its collecting area is around 6 times larger. So in terms of orbit, as I was saying previously, they have very different orbits. So Hubble was orbiting around the Earth, and that meant that sometimes it was in the shadow of both the Earth and the Moon, and that is not ideal for observations. And as I said before, in terms of wavelength range, Hubble observed in the ultraviolet, in the visible, and caught a little bit of infrared, whereas Webb focuses on infrared only. But now, talking about the science surrounding Webb, so there are 4 broad categories that Webb is focusing on. We have the early universe, we have galaxy evolution and formation, we have the life cycle of stars, and then finally exoplanets. And now we'll explain things in a little bit of more detail. So in terms of early universe, you know that the universe is thought to have gone through a series of phase transitions. And so in the last phase transition, the universe was coming out of the dark ages. So the universe was opaque, filled with hydrogen and helium. And then some sources of light started to ionize the medium. And the medium became progressively more ionized and transparent. And this is what is known as the epoch of reionization. But as of currently, we don't know what were the sources of that reionization. We don't even know if it's galaxies, stars, or etc. And so this is one of the main focuses of Webb. It's to find out what were the sources of that reionization, what are their physical properties. So if it was galaxies, it would be galaxies that are very different from Milky Way type galaxies with very different physical properties, and then finally determine when did that reionization occur. So at what redshift. So another focus of Webb is galaxies, galaxy formation and evolution of near galaxy, and also of high redshift galaxies. And one of the problems in galaxy theory is really the star formation rate. Because, as I said before, a problem in astronomy is that dust heavily interferes with observations. And in particular, it interferes with a parameter called star formation rate. And Webb, because it is able to peer through dust, it will finally enable to get good measures of the star formation rate. Moreover, as we will see later, Webb is also really focused on mergers and galactic interactions, and the relation between the supermassive black hole and the host galaxies of the black holes. Okay, sorry. So another goal of Webb is to study the life cycle of stars. So how stars are born, how they evolve, under which conditions, and their death. and how dust affects this process. Moreover, it will also probe the interstellar medium, which is the medium that surrounds stars, and it will also try to study how planetary systems are formed around the stars. And finally, another major goal is also exoplanets observations. So exoplanets, I think you know, it's planets that orbit around other stars. And we want to know if there are any other Earth-type like planets out there, or any solar system type planetary systems. And finally, look for signatures of habitability. Okay, so now I will walk you through some of the observations we already have of Webb. So the first observation is the Southern Ring Nebula, which is predicted to be 2,500 light years away. So as you learned in class, a planetary nebula is basically clouds of gas and dust that are ejected from the red giants, okay, at the end of their stage. And we can actually see in these images the layers of light being ejected from the stars. And so the further the layer of light, the older it was ejected from the star. So with the AstroCamp, we are able to observe. I don't know if you can see, but at the center of the nebula there are two stars. So we are finally able to see the two orbiting stars around each other, and one of them is actually a white dwarf by now. And so this was never seen with Hubble, and was now seen in the first images of the James Webb. So another image was the Karina Nebula. So this nebula is giant clouds of gas and dust where star formation is occurring. And so what is happening here is that it's what it's called cosmic eclipse, and it is ultraviolet light from massive hot young stars that are ionizing the medium. And so the hot ionized gas and dust is actually escaping the nebula into that blue area. And so with the AstroCamp instrument, we are finally able to see hundreds of previously hidden stars. And in the background, we can actually see some new galaxies, which were hidden before as well. And with the MIRI instrument, we can see hot dust and hydrocarbons and other compounds. So this is all new information. So finally, leaving the Milky Way, we go to the Higgs compact group 92. And so this is a visual grouping of 5 galaxies, but only 4 of them are actually interacting via gravitational interactions or any other type of galactic interactions. And we can actually see in the topmost galaxy a black hole which had never seen before and is now very clearly seen. And also in the leftmost galaxy, we can see that the bright core of the galaxy and some individual stars were actually resolved. And this is something that can only be done with such infrared sensitivity like the James Webb has. Also, some structures like tails of gas, dust, and stars and shock waves can also be clearly seen in the image. And this is all a byproduct of the interactions that are happening inside between the galaxies. So in the fourth observation, we have this exoplanet WASP 96b. So this is a hot, puffy, giant exoplanet, much larger than the ones we have in our solar system, that is orbiting around a sun-like star in some far away, very far away, okay? And by measuring the light curve and the transmission spectrum, so the transmission spectrum is basically a comparison between the light from the star as it is filtered by the planet's atmosphere. So comparing that with the unfiltered light of the star. I can explain this later if you want. So by analyzing the transmission spectrum, we were able to find a distinct signature of water, which is very impressive. And also some evidence of some molecules in clouds and haze. So for the final image of the James Webb, and circling back to the beginning of my presentation, we have a deep field. In this case, it is of the galaxy cluster SMACS0723, which is 4.6 billion years away. And we can see that we are observing very faint objects in the infrared that are very distant. So this is the deepest image we have until today of the infrared universe. And thanks to the NIRCam, we can see very faint structures like star clusters. And with the mirroring instrument, we can see the various colors of the galaxies. So we can see blue galaxies. Blue galaxies are the ones that are active, that are forming stars. We can also see plenty of red galaxies. So these are the ones that are very rich in dust. And we can also see some green galaxies, and these are the ones that are rich in hydrocarbons. And we can also see some effects. I don't know if you can see, but there's some arc in the picture, and that is the effect of gravitational lensing. So the light that is coming from objects behind the galaxies is actually being bent by the mass of this galaxy cluster. So the galaxy cluster is so massive that it actually bends rays of light. So I'll just end with this picture, which is a comparison between a Hubble deep field and a Webb deep field. And you can see how much we have improved in terms of infrared sensitivity and detection of faint sources. And so obviously Webb will pave the way for a revolution in astronomy. Either it is by studying the first light and exoplanets, life in other planetary systems. And so this revolution is just getting started, and you and me possibly might be a part of it. And that is where I would like to end my presentation. Thank you.